Hello, everyone. My name is Edward Freeman, and welcome to a primer on the mathematics of machine learning. I'm a rising CS freshman at CMU. I think the purpose of this sort of primer is just to sort of be for people who are getting into CS, or really ML, sorry, but don't have the education of the actual of like basic CS math yet. That would be Calc 3, linear algebra, discrete, stuff like that, statistics, probability. Um, and I think this is really intended for high schoolers and maybe like first year undergrads before you really get into this machine learning. You can like just see what the math looks like, so then it sort of motivates your studying. But yeah, with further ado, let's get ahead. You're not gonna learn much from these slides. I think the whole purpose is really to like prime you and get you interested in the field and show what some stuff is about. Um, it's not the best representation of the field. I think you really need to study it to get a good representation of it. But yeah, I try my best. Let's get into it though. Okay, so the goal of machine learning is to find some sort of pattern or mathematical relationship between input and output data. Um, ML is the way that we achieve AI, which is artificial intelligence. It's data driven. For a long time, AI was sort of algorithm driven or knowledge driven. They say back in the 1950s, but now it's data driven. It's built off of data. Um, a machine learning model, really a model, don't call it a program, a model is trained on data to perform a certain task. So our focus is going to be on a very simple algorithm in ML, linear regression, and we're going to talk about making a linear regression model. Um, so let's talk about our example problem. Our example problem is predicting house prices. So imagine we have some house and we want to turn it into money and see the actual value of the house. Um, we're going to take our data set, and this is a data set of houses. So it has, basic descriptions of the house, and we're going to see if we can turn it into money. Now, again, data is very important to ML people. The features, let's go over some terms. The features or the inputs of our data set are basically what goes into the data, the model itself. So these are all the columns over here. These are the properties of the house. The labels are the output of the model. That's what we're guessing, or that really the label is what exists in the database. So these are all features. These are all features, and then these are the labels for each example or member. Each example member is basically every entry in the data set. In our case, it's every single house that we have in our data set. Um, and yeah, that's sort of the basic rundown of data. Now we get into the math element of it. So this is a linear regression model. It basically just has some sort of parameter, W1, W2, whatever, for each feature in our database. So x1 is basically like, if you go back a page, x1 is like the latitude parameter. And so we take that number and we throw it into our equation. Now, if you see a little I here, the I represents which member in our data set it is. So x to like the second isn't x squared, it's the second member in our data set. If that makes sense. Hopefully it does. Um, so yeah, our y hat of I is our predicted value for a certain example I. An I is a number, right? The weight or learnable parameter of feature one is a weight or a parameter for the feature, which is our input, right? So I think a good example is, let's say feature one is like the square footage of the house. The weight of feature one, the weight of the square footage would be how much money each square foot is worth. So if it's three, then we can assume that every square footage is worth $3 towards our final house price. Um, Another example could be like if feature two right here was the amount of rooms for each house, then the second weight would be, how much each room is worth. So we can say like 1,000. Now, we also add some little constant at the end, and we can really turn it into a vector if you know in linear algebra. This is just a simple dot product. Um, so this is our entire data set in one prediction. We don't really do this that much, but I think it just shows how, there's a lot of linear algebra behind all this. Um, again, the big example here is we have these parameters, and they basically are the mathematical connection from the real life output or input and output. So we're taking our feature, we have some parameter that is going to change when we train our model, and that parameter really connects the feature to the actual output. It sees how much the feature is valued, if that makes sense. So then we get into the training phase. Uh, our training phase is split up into epochs. Each epoch is an iteration through the entire database. or mostly in relation to the entire database. The first thing we do is we compute our prediction or our y hat for each example, and then we compute how far off our model is, and that's the error. So what we're doing is we're taking our predicted value and we're subtracting the actual value in the database, the label. We're squaring it and then doing the square root, and then we can see how far off our model was. Um, we also we create a cost function dependent on our model parameters that computes the root mean squared error, the RSME. And what this does is goes through our entire database and basically finds the average error or the mean error. Um, One thing I want to point out is, like I said earlier, J, the cost function J is dependent on our model parameters. It's not dependent on our features in the database. Now this is gonna come up useful later. But you can think of JWB as basically the how far off our model is for the entire database, right? It's a metric, and it's the big idea is dependent on model parameters. Then we get into gradient descent. Now, if you haven't taken calculus, this can be a little hard to understand, but basically the gradient shows the the direction of greatest increase. Basically, where our object or where our point should go that shows the greatest increase on a function curve, right? Now, if our goal is to minimize the cost function j, what we can do is we can take the negative gradient, and that shows where we need to decrease, or where which direction is the greatest decrease. So really, this exists in like 20 dimensions. What we're doing is we're basically saying, okay, where do we need to change our model parameters that will basically make it so our function decreases the most? It's an optimization problem if you know that from calculus. Now the golden equation is we take our new parameter and we set it equal to our old parameter minus a little bit of the gradient. Now the gradient here is multiplied times some learning rate. The learning rate is a decimal number, and it basically makes it so we take smaller steps. Um, the whole idea of gradient descent is it uses the power of calculus to minimize a function. That's what gradient descent is. And what we're doing is we're taking these small these small positive or negative nudges in the sorry these small nudges in the positive or negative direction. I'm reading up my words too much. To achieve a lower value of our average error. We're basically saying, okay, where do we need to change? And it sounds magical, but if you know calculus, it's not really. It's just basic calc. We're basically saying, okay, where do we need to change our model parameters to have the greatest decrease? Now, I sort of want to go through this little process where we take some sort of basic feature of basic ML and we sort of explore the problems with it, and then we present research at the end. Now, one issue is we don't always have a picture of the graph. Um, this is nice when we have two variables, but really we usually have like 10 variables. So it's a 10-dimensional graph. We can't visualize that. We don't really know what that looks like. So one thing I want to point out is we don't really know we don't really know what path we're taking. We can't All we can see is what's going on at each point or where we need to go. We don't If we're at this point right here, we don't know that there's a minimum right here. We just eventually take the descent and we basically find that, okay, the minimum is right here. Depending on the learning rate, the little alpha symbol, um, our function can overshoot our minimum or go slow. So if it's too low, then we're only going to make small changes, and that just takes too much computation time. And too much computation time isn't good. We don't want that. Um, just right is when our function is has a learning rate that's not too high and not too slow, and that just finds the minimum very easily. As you can see, the gradient decreases over time. So when we get to the very bottom of the graph, we're gonna have a very small nudge that we're going back and forth because our gradient is like horizontal at that point. So it's basically zero. Now, then we get to a very extreme example where the gradient descent is too high. In this case, if you look at our gradient vector right here, at this point, if it's too high, then if we subtract too much of this gradient vector from our point, we're going to overshoot the minimum, and that happens a lot. It's called divergency. The other sort of big issue with gradient descent is we don't really know if we have a minimum, if our minimum is a global. So if we do gradient descent right here, basically we can assume that our function will go this way, it will get to the very bottom, and then it might go back and forth. It might trudge back and forth until it basically finds that, okay, it's at the spot, right? Once we've gone through enough epochs, we basically say, okay, if our parameters aren't changing that much, I think we're at a good point, right? The issue though is there also exists a whole other minimum right here that we didn't even see, and that's because we started right here. If we started the point right here, we would have found that minimum. If we started the point right here, we would have found this minimum. So we don't really know if a minimum is global or not, and that's kind of an issue. Now I think that research in ML is really important, I think that once you get past like the basic concepts in the slideshow, it's mostly most of the cool ideas are in research. And so you need to learn how to read research papers. I'm gonna present the probably one of the most impactful papers of the past. Um, I don't know, probably the past century, at least in the 21st century, which is the Atom optimization method. It has over 200,000 citations. That's an insane amount. Um, and in the Atom paper, basically what it says is it updates parameters based on previous gradients. So not only are we taking the first gradient, but we're also taking the second gradient. So this v of t minus one is basically the v is the average of all the gradients along a curve, and we're taking the previous gradient. These are some sort of hyperparameter that we can assign to it, some coefficient, and we're taking the previous gradients in both these problems, and we're basically taking those into account. And then we have this sort of change in parameters that we should take, and we account the and here what we're doing is that's different is we're taking the previous gradients into account. It amplifies what we call the big hill effect, where like if the past three gradients said to go in a certain direction and this gradient saying to go in a certain direction, then we're gonna go in that direction very fast, which just speeds up training. Um, we also have dedicated learning rates for each parameter, which just makes training better. Um, again, this is very like a quick summary of the Atom paper, but it's a really good paper, and I think that this shows how like the pastor slides just showed an issue with a very basic machine learning process, and the Atom paper attempt to solve some of those issues, not all of them, but some of those issues. But then we get to the issues of ML, and the thing is, basic ML models are very shallow. They can't find complex relationships in data. There's not a little much application outside of statistics, and the basic ML algorithms like linear regression tend to bottleneck performance when we increase data and compute power. So there's basically a fall off that older learning algorithms will take. That's why we need deep learning. Deep learning is a field in AI that basically is uses neural networks or inspired off the human neural networks to do learning, to do machine learning. Um, Deep learning finds much more complex relationships and can use much more data. So neural networks have a bunch of neurons in it, and neurons are basically a bunch of tiny math equations. Now the input layer for our neural network is basically all of our data features, and the output can be one or multiple neurons is our final prediction. Now each neuron, really the perceptron, is basically our old linear regression model where all the inputs to the model are the previous neuron's outputs right here, and we basically take that final value and we throw it into an activation function. Now the activation function basically adds some sort of non-linear complex relationship to our model, which adds more complexity and helps us find more useful features. So these are a list of some activation functions we have. They all do different things, but overall that the big difference is before we had one equation, and now we have a much more complex process where each one of these is one linear regression equation that we throw into an activation function, and then we send it to the next layer. Um, Now neurons can be activated or fired. Um, if a neuron, there's a certain threshold that neurons exist where if it goes over that threshold, then the neuron will actually send the value to the next layer. Really, if it's around zero, that means that the neuron isn't contributing much to the next neuron, so therefore it doesn't really matter that much. But the big idea is we'll send data through the network. Different neurons will send different values. Some really close to zero, some really far from zero, and then eventually we'll get to that final prediction. Now, um, before we discuss how we actually learn all the parameters for each one of these neurons, I think it's important to talk about the output of a neural network. Um, the first case is classification. This is where we're not predicting like an actual value, we're predicting classes. We're trying to classify data. For binary classification, the output is basically the probability of like a yes or no, true or false question. So the questions we ask are, is input a dog? And then the output would be the probability of what the neural network thinks that it's a dog. Not the actual probability in nature, but what the neural network thinks. Um, for multi-class questions, we basically have the output of the probability for each class. So P of A represents the probability of it being class A. If we ask the example, what animal is this, and we sent all the data through our neural network, the output of would be the array of probabilities for each class. So the probability of it being a cat, dog, or horse. All these probabilities add up to one. That's the really special part about neural networks is because they all add up to one, there's a fixed size, so they can't all just be infinite, and therefore we have to choose one of these outputs as our final prediction. Whatever's the highest probability, that's our final prediction, right? So if the neural network's like probability of it being a cat says 0.7, then we probably know that that is what the neural network thinks it is. Um, uh, we also have regression. So earlier we had linear regression, which basically just like again these are house prices. Now we have regression again, which are just actual straight numerical values. But here we're going through a much more complex process where we're basically taking all of our data, then throwing into an activation function for each one of these neurons, and then doing it again. So it's just much more complex. You can imagine that it's like linear regression on crack plus activation functions, which have that added complexity. Then we get to learning neural networks, and at the end we can't just do gradient descent like we did earlier because there's so many more parameters for each neuron. And how do we know which parameters contributed the most to the final output since there's so many more parameters now? The way we do that is we do backpropagation. So you remember the chain rule? If you took Calc 3 and maybe Calc 1, you can maybe understand this. But the multivariate chain rule is basically um, takes the derivative of the whole thing and splits it up between the derivative of whatever the function is dependent on. So here, the function is dependent on two other variables, x and y. The derivative of this function is basically the derivative of x and the derivative of y, sort of, when it's dependent on x. Now, we apply the chain rule to the entire data set, and that's how we get all of the sort of gradients for each parameter. And in that case, we just go and we sort of back propagate. So we take our error, we have the error at the front, we sort of go all the way back and figure out which parameters had the certain gradients, which one contributed the most of the error, and then we go back and update them to the very end because each one of these parameters here is really dependent on these values, which is really dependent on these parameters here. So as you can see, there's a whole like recursive chain. Um, Three blue, one brown. It's a great video on this topic. Now that we're nearing the end, I sort of want to like highlight that that's not really what all of deep learning looks like. There's all these really cool architectures in deep learning where there are all these different unique approaches to the field. It's not like just a bunch of like linear regression equations. Um, we have structures. We have these architectures. Convolutional networks. That's like the second uh, architecture you'll learn about. That has to do with images and image processing. So it uses these things called convolutional layers, which basically extract information from certain points on the image. We also have GANs, which work on generation. They have a generator. We basically play a game of generator and discriminator, where the generator will generate fake examples, and the discriminator has to choose between the real and fake ones. And then once the discriminator gets good, the GAN generates more fake examples to try to fool the discriminator, which is a really interesting process. We have transformers, which are taking over AI. They use the attention mechanism, and the attention basically just figures out how much each input in a sequence affects all the other inputs, which is again really good for any sequential task, really good for LLMs and generation. We also have autoencoders, which basically find latent spaces. They do dimensionality reduction, which again are really useful. Um, as I wrap this up, I also want to give a motivation. A lot of people are interested in AI right now, and sometimes they might lose their motivation in any math class. But I want to tell you that every single math class can be applied to AI. Um, as you can see by this chart, there's so much AI that exists sorry, there's so much math that exists in AI that I think that if you enjoy math, it's really the field for you. There's so much cool stuff you can do. I think getting started, there's three good resources. Supervised learning. We have the Andrew Ng course. It's a Coursera course. It's free. It will ask you to pay, but you don't have to pay. You can get past that. Great videos, great introduction. Then we have the three blue, one brown sort of intuitive series on neural networks. That's a great series. I think once you get past these two, that's when you start have to learn the. Sorry, my headset died. That was kind of embarrassing. Um, I think once you get past the Andrew Ng and the three blue and brown videos, I think it's more important to learn the math. That's what I did. Start focusing on the math, and then you can jump into the two textbooks that I have here, which are great. One is more like I guess more traditional textbook based, and the other one is coding and theory. Yeah, it's really good. I think the best resource is to start doing Python, learn the libraries, and just start coding um, alongside your studying. Yeah, that's about it. Thank you all so much. Have a good time.